All right. So after Eulerian, we're going to look at Hamiltonian and semi-Hamiltonian graphs. Right. Now, basically on the whiteboard, I've summed it all up. Hamiltonian and semi-Hamiltonian. Hamiltonian is considered as closed. Semi-Hamiltonian is open. The summary is visit every vertex once. No repeating edges. That's what you need for Hamiltonian. All right? Now, so by the end of the lesson, I would like all of you to understand what Hamiltonian and semi-Hamiltonian graphs are. You should be able to distinguish between Hamiltonian and semi-Hamiltonian graph and able to determine a graph is Hamiltonian or semi-Hamiltonian and use that to solve your problems. All right? Now, remember I showed you this summary. We talk about walk, trail, and path. Now, the thing is I show you the word circuit, but in SCASA, they don't actually use the word circuit. All right? They use semi-Eulerian trail and Eulerian trail, which is, okay, to me is, all right. So just make sure that you know what Eulerian and semi-Eulerian is. All right, trail, edges cannot be repeated, but vertices can be repeated. Now we're going to look at path now. All right, we've got open path and closed path. This time we're going to look at path which takes you through all the vertices. All right, a path can be an open path. Let's say you've got A, B, C, D, 4 vertices. You go through A, B, C. That's an open path, right? But A, B, C, D would be a Hamiltonian because it's going through every vertices, but not repeating the edges. All right, and not repeating the vertices. So let's have a look at Hamiltonian. Let's start off with Hamiltonian cycle. So if a Hamiltonian path is closed, begins and ends at the same vertex, it is said to be a Hamiltonian cycle. So in other words, a Hamiltonian cycle is a cycle that includes every vertex in the graph exactly once. The word exactly once is important and begins and ends at the same vertex. So if a graph has a Hamiltonian cycle, it also has a Hamiltonian path. All right? I'm using the word Hamiltonian path at the moment because I'll tell you what Hamiltonian path is. Now, SCASA has taken the definition of Hamiltonian path out. All right? So basically, what you need to think about a Hamiltonian path is just a path that connects every vertices, every vertex once, and it's open. All right? Yeah? So the last one, I'm just putting in for your information. That's why I did not put in a color. But the first two is quite important for you to understand. All right, Hamiltonian cycle. And it's a closed path. So Hamiltonian cycle is closed. All right, it's closed. Now some examples. So here, the path A, B, E, D, C. Sorry? Yeah, sorry. Can I move on? All right, so here's an example for you. The path A, B, E, D, C, A. So I started from A. A, B, E, D, C, and then I've gone all the way back to A. All right, that is a Hamiltonian cycle. It's a closed path, correct? And what it does, it visited every single vertex once, but there's no repeating edges. Yeah? Happy with that? So you need to see that there's a Hamiltonian cycle and this graph is a Hamiltonian graph. Alright? There are many other Hamiltonian cycles in there. Alright? You could go, for example, A, B, E, D, hang on. Oh, this is going to be the interesting one. How do I do it? You can go backwards. You can go A, C, D, B, E, A as well. That's another one, right? A, C, B, E, A, D, A. Let me use a pen. So if I go this way, and then here, here, this way, B, E, and A. That's also a Hamiltonian path, correct? Yeah? So what I'm doing here, the way I'm doing it is how you have to, if you're asked to draw it in an exam, this is how you indicate. Because you cannot use a highlighter in the exam, it will not scan out. You've got to use a squiggly line to show that. All right? So this is another possible Hamiltonian cycle. Now, these are all the possible ones that I've done for you. You can see that when you're answering question, all you need is to select one. You don't have to select every single one. All right, just one. Make sure that all the vertices are visited once and no repeated edges. All right, Hamiltonian graph. So, first one, the graph is not Hamiltonian or semi-Hamiltonian. I will go through semi-Hamiltonian a little bit more carefully in a few minutes. It is not possible to visit every vertex once. All right, second one is a semi-Hamiltonian graph because you can visit all the vertices one and there's no Hamiltonian cycle. So let's start from C. I can go from C, B, A to D. There's no closed path, correct? There's only open. You are going one way, or you can go D, A, B, right? Or you can go the other way is A, D, and C. Yeah? So that's a semi-Hamiltonian graph. This, in your book, is referred to as Hamiltonian path. Here, this path has a Hamiltonian cycle, therefore, it is a Hamiltonian graph. This is the Hamiltonian cycle. All right? So basically, you're traveling from A, B, C to D, or A, D, C to B, or B, C, D, A, or whatever. There's no actual starting point. All right? You can start anywhere you like. Now, semi-Hamiltonian graph. A semi-Hamiltonian graph is a connected graph that includes every vertex in the graph exactly once and starts and ends at different vertices. So here, you can see that I have changed the color of that. That is the path that you can take A, B, C, D, E, F, and G. So that is actually one open path and it's semi-Hamiltonian. It's not closed, it's open. It starts from one vertex and then visited at all the other vertices and finish at the other vertex. All right? So that's semi-Hamiltonian graph. All right. Now, this is the other one. Now, notice that I've gone through the bridge. All right. Remember, this is called a bridge. If that's not there, there is no Hamiltonian graph at all because you cannot visit every vertex once. All right. It makes it two subgraphs. So remember, it has to be a connected graph. All Hamiltonian and Eulerian graph has to be a connected graph. Right? More examples. So these are all semi-Hamiltonian graphs. It starts and ends at different vertices. So the other thing that it does is you'll find that the book uses the word Hamiltonian path. It just means an open path which connects all the vertices. That's all. No repeat edges. All right. Like I say, Scarza has taken out the definition of Hamiltonian path, but it's still on all the books and all the past exam papers. So when you look at past exam papers or the books, Hamiltonian path means an open path with which visit all the vertices. All right, no repeat. All right, this is another one. Semi-Hamiltonian graph. Open path which includes every vertex one, begins and ends at different vertices. All right, the word path shouldn't be there. I'm not sure why. All right, so note that the other one, what I say is that's not unique. There are many other paths, so you can always name any one you like. Just like what I explained, if the bridge D is removed, the graph will become disconnected graph, and a Hamiltonian cycle will no longer exist. All right. The reason is you're considering the whole graph. All right. Here, as soon as that's disconnected, you cannot go from D to E. All right. By itself, if this is a graph by itself, without these three little things, there is a Hamiltonian cycle, correct? Yeah, by itself. But because it's a subgraph from that, you can't say that there's a Hamiltonian graph. All right, properties of Hamiltonian graph. Hamiltonian graphs are connected graphs. All Hamiltonian cycle can be converted to an open path by removing one of its edges. So that means it can, with a Hamiltonian graph, it also consists of a semi-Hamiltonian graph. Because you don't have to go all the way back, you can take one of the edge out, which makes it semi-Hamiltonian. Now, an open path which visits every vertices can be converted to a Hamiltonian cycle if and only if the endpoints of a Hamiltonian are adjacent. So you may have a situation like this. And that is your semi-Hamiltonian graph, correct? Yeah? So this one, an open path which visits every vertices can be converted into a Hamiltonian cycle if and only if the endpoints are of a Hamiltonian path are adjacent. So, semi-Hamiltonian path are adjacent, sorry. So you can actually connect it that way. All right? If you were asked a question like this, how would you convert it? You have to connect the endpoint. So once you connected that, that becomes a cycle, correct? Yeah? So I've got to edit that. Now, all complete graphs, Kn, are Hamiltonian. Complete bipartite graphs which have the same number of vertices in each group are Hamiltonian. Right, remember your bipartite graph? So if you've got that, the complete bipartite graph. Right, you can see that it will be Hamiltonian. Start from here, I can go to here, come here, that way, that way, that way, and back there. Right? There is no repeating of vertices at all, and there's no repeating of edges. So think about complete bipartite graph. Complete means this one has to be connected to this, has to be connected to that, has to be connected to that. All right. Make sure that you know what bipartite graph is. All right. All right. Determine if a graph is Hamiltonian or semi-Hamiltonian. It's not like Eulerian, where there's a test. Where Eulerian, if you've got all even vertices, you know that's Eulerian. And graph with exactly two odd vertices is semi-Eulerian. But there's no general test for determining the presence of Hamiltonian path or cycles. We need to check every vertex. This is a pain in the butt. you really have to trace it. And you've got to be careful tracing it. Sometimes the graph can be so complicated. All right? And then for graph that's Hamiltonian or semi-Hamiltonian, it must be a connected graph. And it can have no more than 2 vertices of degree 1. Which means you could have something like this. Right? So if I've got this is connected, that is a bridge there. So that means there's no more than 2 vertices of degree 1. So that's 1. Well, how do I do it? Yep, this way. I can do it this way and do it this way. So that's degree of 1 and degree of 1, 2 vertices of degree of 1. All right? Now, let's have a look at this. Can you list an open path which includes every vertices for the graph shown? In Clark, it will be referred to as Hamiltonian path. All right? So any other books that you use, it will be referred to as a Hamiltonian path. So now I want is an open path which includes every vertices. And this is a semi-Hamiltonian. All right? You don't want a closed path, you want an open path. So you can start from anywhere. All right? Say if I start from D. Oops. What am I doing? So if I start from D. All right? So I can go from A, go G, H, C, A, B, E, F, and G. That's open path, correct? You're not repeating any vertex at all. Or you can start from F. F. Oops. No, I can't actually start from F, can I? If I start from F, nah, can't do that. So if I start from
you have to come back.
F, you have to do it the other way. So if I start from F, I've got to go that way. All right? Yeah? That's the other way of doing it. So, the last one I should have connected because it's open path. Yep. You can see that. So it really doesn't matter. You don't have to start particularly from A or from B or C or whatever, unless you are specifically asked to do that. You can start from anyone. So in this case, if you are listing an open path, I can go from F, G, D, H, C, A, B, E. This is how you list it. Happy with it? All right, let's move on to the next one. List a Hamiltonian cycle for the graph shown. If you are listing, it may pay for you to just highlight. This is a Hamiltonian cycle. So I'm listing it. I can start from E, F, G, J, I, H, D, C, B, A. All right? You can start from any point. It really doesn't matter. And go back to E because it's a cycle. Make sure that you've got that and that the same vertex. Make sure you have that. All right? You cannot stop at that. That's open. That's closed. That's a cycle. All right. Let's have a look at this example. A salesman is traveling to 7 country towns to sell flour to the local bakeries. A map of the town is shown below with the vertices representing the towns and the edges representing the route connecting the towns. The salesman wants to travel from town A to visit every town once on his journey and then return back to town A. What type of walk is this example of? All right, walk is general term. So here, he will ask you a question. What is it? How do you define that? What is the definition? What is the same one? Hamiltonian cycle, thank you. That's correct.
Would you say semi-Hamiltonian?
Hamiltonian cycle.
So just the Hamiltonian part. I think so.
Describe a route the salesman could take. So this time specifically, you have to start from A, correct? So again, like I say, in the exam, if you're not asked to indicate in there, it's pretty straightforward if you could actually highlight it. Makes life a little bit easier for you, right? So that's one that you can do, use. So once you know that, you can just write down A, B, C, D, E, F, G, H, I. Alright, this is just an example. It's a pretty straightforward example. Some of them will be a lot more complicated than that in the exam. And you can now list the ages that the salesmen do not travel on, which is AC, CE, CG, and HF. Now, if you do it the other way, say if you have something slightly different, you decided to do this, starting from A, C, D, E, G, F, H. Oh no, I can't do that. Can I do anything else? Probably not. So what the way I've selected would be the best way. Alright? Sometimes there's just one straightforward answer. Sometimes they are not. Sometimes you can have several answers. Alright, that's all I have for you today. Just make sure that you do some exercises from club. Tomorrow we'll do some revision. It should be club. Let me think. Club exercise 8F, I think.